to our highlight of today, which is our talk by Doug Schouten. So Doug Schouten is the Chief Technology Officer and co-founder of Ideon Technologies. He is a global leader in Muon Tomography and one of the few people in the world with the expertise to turn muon research into industrial problems solved. Doug holds a BSc in Physics and Computer Science from UBC and a PhD in Subatomic Physics from SFU. Doug has extensive experience in computer simulation, data analysis, and statistical inference, including machine learning methods and detector physics. With that, I will turn this over to you, Doug.
Thanks, Ross. I'm glad to hear I'm the highlight of the meeting.
Yes, absolutely.
So thanks a lot for the introduction and thanks for the invitation as well. I was surprised to hear from Dennis that it's been so long since we last presented to the BCGS. And I'm happy to update you all on some of the advances that we've been making in cosmic ray muon tomography. There we go. I think a good analog to start with, understanding that there are those in the audience, perhaps who have seen some presentations on this in the past, and probably those who are more new to the technology, is to start with an analogy that we're all familiar with, and that is medical x-rays, which have really transformed medicine, allowing doctors to see directly inside the human body in a straight line imaging way that allows to understand what's going on before applying invasive procedures. In a similar way, cosmic rays enable us to directly probe inside the Earth in a directional way to map density contrast throughout the subsurface. So the agenda for the talk has a couple of parts. I think I'll start at a high level, looking at muon tomography, understanding what it is, how it works, and why we think it's a game changer. I'll introduce Ideon Technologies. I think last time we talked, we weren't Ideon yet. So who we are, what we're doing, and what drives us. And then I'll circle back and look into the methodology in more detail. In particular, looking at some case studies and field trials, some recent ones, including with some overseas partners. And then I'll look at the borehole detectors in upcoming field trials. So we have spent a long time getting to this point, and we're very excited to share with you the progress we've been making on that technology. And then I'll wrap up with a summary and some more information on applications and how this can be brought to bear in mineral exploration and mining writ large. So with no further ado, I'll proceed to introduce muon tomography. And I think it's a good place to start is with the word muon. So what are cosmic ray muons? Briefly, they're a passive signal source coming from space that enables us to do subsurface density imaging. A muon is a naturally occurring subatomic particle, very much like an electron, and it's created in the end as a result of supernova explosions in space. The resultant cosmic rays out of these explosions, which are primarily protons and helium nuclei, emanate at the speed of light and interact with matter in the upper atmosphere of the Earth. And this initiates a whole cascade of nuclear secondaries. So you can see a sort of artistic rendition of nuclear showers propagating in the atmosphere at various points on the Earth. The majority of these subatomic particles are filtered out or decay very, very quickly, such that at the surface of the Earth, the preponderance of cosmic ray radiation is comprised of muons at about 95%. These muons then penetrate underground, and they lose energy at a rate that's proportional to the density of the material they're going through. And so eventually they lose enough energy that they're stopped, or they actually decay. And what happens then is that we can sort of map the intensity, the directional intensity underground. And that directional intensity is related directly to the average density along a path, a straight line path from the detector to the surface in any given direction. This is essentially muon radiography, very similar to X-ray radiography. We can then combine multiple detector images to map the density in 3D, and that's muon tomography. So as a point of reference, muons are passing through you right now at about once per minute for every square centimeter, or about once per minute for the area of your thumbnail. Looking at this in more detail applied to muon mineral exploration, we make the assumption that muons travel in straight lines, which is a very valid assumption. And we can then propagate backwards from the detectors, as I mentioned, to look at the directional intensity in a 60-degree field of view in all directions from a detector located, in this case, down a borehole. This allows us to calculate for every muon that passes through the origin of the muon, so where it came from, the time that it arrived, and the position of the detector, the position where it hit in the detector. And we can then push this data up to the surface and then link to our servers here in Vancouver via satellite or cell link. And we can generate radiographic images, which are basically scanning that directional intensity in all directions above the muon detectors. So these X-ray-like images are acquired over a period of time. We can see this going live, essentially, as the data is collected, and we can sort of manipulate or redesign the survey as things emerge in the data, or wait till the projected end of the survey design. We can then combine these data into a subsurface model using classic inversion approaches, as well as other more advanced ones. And we deliver these to our clients to basically map density in 3D and also to combine with other geophysical data sets. So we have quite a long history from the beginning of this technology being applied to mineral exploration. That really came from geophysics, actually. So a physicist from Cameco, Brian Powell, reached out to Triumph Innovations. He'd been reading some papers on applying Muon Tomography back in the early 2000s to volcanology, which was in a nascent application and research field. And he asked if this could be also applied to mineral exploration. Out of that, an internal research program was launched at Triumph that culminated in the production of our V1 Muon detectors, or version 1. And then we spun off a company in 2013, which was a whole subsidiary of Triumph Innovations. And this furthered the capability in developing a version 2 detector, as well as really advancing the technology on the physics modeling and inversion capability side, as well as completing a number of field trials that proved the capability in a number of applications. In early 2020, we relaunched as Ideon Technologies, fully spinning out and becoming a wholly independent corporation out of Triumph. We had a new CEO join, and we really ramped up our borehole detector development. In June of 2020, we closed seed round financing in the midst of a COVID epidemic. Went surprisingly well. And we just recently announced our first deployment partner with our borehole Muon Tomography technology. So we're now at the cusp of bringing this to bear and releasing this commercially. So it's been a long time coming from the very early stages of the R&D to where we are now. And we have a lot of generous sponsors from the government sector that have really supported us, as well as from the sort of incubator tech sector in Vancouver, as well as academic partners that have really partnered with us to help us bring this technology forward. Not to mention the various industrial partners that have done early testing and field trials that have really proven the capability. The context of where we're headed is what we've noticed coming out of the industry is exploration is getting harder and deposits are getting deeper. Over the past 10 years, ore discoveries are down 75%. The meters drilled per discovery is up almost a factor of 2, and the cost per discovery a factor of almost 4. So over the past 10 years, about $200 million has been invested in exploration with an ROI of negative 45%, so only 110 billion added in economic reserves. So in this context, we think that Muon Tomography is a significant advance that will add value to the exploration cycle, as well as the whole mining chain. So Ideon Technology has a mission and a vision, and that vision is to transform subsurface discovery by delivering subsurface intelligence that accelerates the world's transition to low impact mining. Bit of a mouthful. We're really excited about this vision and mission. Speaking more colloquially, delivering this subsurface intelligence with high fidelity, high resolution imaging will allow significant improvements, we think, in both exploration returns and also in being able to better map and understand what's going on in the subsurface during the mine resource delineation and mine planning stages. To do this, we have a discovery platform we're building out. A key part of that, of course, is the advanced detectors that we'll be talking about more significantly later on in this presentation. But it begins really with site data and modeling. And we've developed quite an extensive suite of software tools to do forward modeling for various potential fields, as well as Muon Tomography, and to really optimize survey design in terms of maximizing information gain versus cost. We have, of course, advanced detectors we've talked about. I've hinted at 3 versions of them, which are patented internationally. And inversion technologies, both the traditional voxel type inversions and surface mesh inversions that also allow us to do hypothesis testing and certainty analysis, as well as combination with other potential fields and geophysical data. A big part of the feature, we think, is artificial intelligence in delivering improved interpretation of disparate geophysical data. Really guided, of course, by human intelligence and geological know-how, but we think there's a big opportunity here, and we've already seen that internally in our programs. And then in terms of target visualization, really mapping density in 3D and providing target and interpretations to our clients. We've had 3 generations of detector development. I've mentioned the V1 already in the context of the development at Triumph. The compact detector was developed more recently, circa 2017. And this was a compact detector for near-surface boreholes, both as a miniaturization phase to getting to the borehole detector, which has been in the forefront of our plans for some years, but also in terms of providing a solution to a client that had a particular need. So this was field tested and proven very capable and really helped us to de-risk the next stage, which was to further reduce the physical form factor, culminating with a total 50 times miniaturization effort. And we're very nearly there in the midst of testing out our systems. So now that I've introduced sort of Muon Tomography at a high level and Ideon Technologies, I think it's worthwhile to circle back a little bit and look at the methodology in more detail, including some of the case studies that are highly relevant. So the Geophysics Basis is summarized with 3 graphs, really. I'll explain them in more detail, but really we start with the surface spectrum, and we propagate that through a model of muon absorption in matter. And this gives us a prediction of muon intensity underground, or a model of muon intensity underground. So for any rock depth that is sort of integrated density or density times path length underground, we can calculate what the muon intensity should be. And you can see sort of a theoretical model, which is the solid line compared to a host of measurements from research labs around the world over some decades of research. And of course, we can invert this relationship given a measured intensity to find a corresponding rock depth, which is essentially a measure of the average density. Looking a little more detail at these figures, the surface spectrum shows a host of measurement data from the early 60s all the way up to the 2010 era. And this is coming from especially particle physics research, where muon, cosmic ray muons are often a background to more interesting research. And there's been a dedicated effort to map the energy of muons as they arrive at the surface and the rate for each given energy. The propagation through the models for muon absorption in matter is very mature. We've used this for decades in muon physics research and more generally in particle physics research, and is controlled at better than 1% level over a broad range of energies and matter or material. So from a scientific perspective, the geophysical method is arriving out of decades of subatomic physics research that has been developed for quite different purposes, but is nonetheless very useful for us. One thing that differentiates muon tomography from other geophysics methods is the fact that muons are discrete particles. So if we look at a detector and a section of solid angle coming from the detector up to the surface, that subtends some volume of rock. And we can count how many muons arrive within that solid angle, which is basically a range of angles, to the detector over a given period of time. And that's a direct measure of the muon flux, or muon intensity underground, which is then directly proportional to the density of the rock subtended by that solid angle section. And so we can map that density, so represent each of these solid angle sections as a pixel in a detector intensity image. And each pixel is just a direct measurement of the muon intensity in a given direction. I've purposely shown it to be a quite scattered and noisy image here, speckly, and that's because muons are discrete quantities. They arrive at random intervals, and over any given exposure time, there will be a stochastic variation in the number of muons that arrive, even though the rate is well controlled or well determined. Over time, the statistical fluctuations, relatively speaking, dampen out, and the true underlying geology or average density emerges in the radiographic image. I mentioned at the beginning of this slide that a good analog for understanding this technology is to compare it to X-rays, and there's a lot of similarities as well as some important dissimilarities. So the penetration depth for muons is hundreds of meters. In fact, speaking very carefully, it can extend multiple kilometers deep. The spatial resolution is sort of meter scale, and the density resolution varies, of course, with depth and geometry of the survey, et cetera, but a good rule of thumb is 0.1 to 0.2 grams per cc. An interesting differentiation between cosmic ray muons and many other geophysics and also X-rays is that it's a passive or natural background source compared to active. So there's really no safety concerns or cost associated with the source itself. And the imaging time can vary from weeks to months, depending very sensitively on the depth of the survey, whereas typically in most X-ray scans, we're talking much less than a second to get significant exposure. So Muon survey works at a high level in 4 simple steps. We deploy the detectors down a borehole or in a mine gallery, taking 1 to 2 days to do this. Then we wait. We detect muons over a period of weeks to months. And these muons arrive at random times from all directions over that period. And we're sensitive to sort of muons passing through the detectors in nanosecond or picosecond timescales. So very fast electronics to be able to capture these data as they come in and continuously monitoring. And for every muon that passes through, we record where it came from. So we track it with some high resolution. We can process this data continuously then by uploading it to our servers. But indeed, if we would collect data over a whole period of months, the processing time, because it's a relatively simple straight line imaging process, is only minutes to at most an hour to process a whole set. And we can then output a map, a radiographic scan of density in each direction. Because it's also straight line imaging, as I alluded to already, the data inversion is also relatively simple. So running an inversion from Muon Tomography data by itself is minutes to at most hours to collect data from, or to combine data from a whole set of detectors and generate a high fidelity 3D density profile. Once we incorporate other geophysical data in the joint inversion, it can become, of course, significantly longer because of the issues with other inversion types, but certainly the Muon Tomography inversion itself is relatively straightforward from a computational complexity perspective. There's a couple of approaches to the tomography. The first is the voxel-based, where we divide the imaging volume into blocks of 6 sides. And the idea is to go from a radiographic image shown in the top right. So you can see in this example, we have a bunch of 3 sensor locations, essentially, looking at density anomalies. And you can see a couple of significant anomalies in the images. And to reconstruct those 3D or those 2D maps into a joint sort of 3D interpretation of all of that data, what we do is we use the muon data in those radiographic maps to determine the density in each block. This voxel-based approach has a very similar problem formulation for potential fields. I'm sure many are familiar with it from the UBC GIF codes, where we have a data misfit term and a sort of model objective term that forces the inversion solution to be smooth and sort of picks out one out of the infinite number of them, given the fact that there's many more unknowns than data constraints in this sort of problem formulation. Having then derived a 3D distribution of density in a imaging space, we can then look at inversion isosurfaces, for example, selecting surfaces of constant density and pick out spatial maps or spatial understanding of the bodies of interest underground. Another approach is to use a structured mesh. And this is rooted in the notion that the voxel inversion, as I mentioned, is highly underdetermined. And in a way to avoid the complications or the mathematical ambiguities involved in the underdeterminedness of it, the smoothness constraints, for example, that are often applied are not really geologically rooted. In many cases, we have sharp contacts between geological bodies and not a continuous gradation of rock properties. And so what we've developed as well at Ideon is a way to basically form an unstructured mesh with a series of interconnected vertices and then vary the positions of these vertices to best fit to the Muon data. So if you look at an example here in a modeling case study, we have the blue, sort of a thin sulfide lens going from east to west, very narrow, sort of 10 to 15 meters across and only a few meters thick. And if you compare that to the green, which is the fitted model coming from synthetic Muon data that's taking into account all of the noise sources inherent in the data, you can see laterally very, very good correspondence between the fitted mesh and the true underlying input model. And this, if we look at the thickness of the deposit mapping over this entire strike length of 300 meters, using only, in this case, actually 3 borehole detectors, or 3 boreholes, you can see a very good correlation between the fitted thickness over the whole structured mesh and the model thickness. And the correlation coefficient is high, and the resolution is about 2 meters spatial or thickness resolution. Because we're also dramatically reducing the number of free parameters in this formulation of the problem, this allows us to do hypothesis testing on a suite of geological models, and that allows us to quantify the certainty of the result in a very quantitative way with high target sensitivity. So instead of having sort of an amorphous blob that emerges in our 3D voxel inversion, whose provenance is sort of uncertain, whether it's statistically or systematically relevant, or if it's an artifact of some data uncertainty, we can directly put in all of the parameters related to systematic and statistical uncertainties into this model fit and come up with a robust understanding of how significant a target is. So with that arming, I'd like to transition into looking at some case studies from most recently to later in the past. And the first one I'll address is one that you probably haven't seen, having just completed it. This is at the Cliffs mine in Australia, working with BHP. So the Cliffs deposit is an underground narrow vein nickel deposit about 700 kilometers northeast of Perth. It's near other significant nickel sulfide deposits, Mount Keith and Perseverance, among others. And you can see an image of it shown in the bottom, which is looks like a sort of a thin sheet, vertically disposed. And it's about 5 meters thick at various points, sort of 3 to 8 meters maximal range. So we deployed 5 detectors in the 362 level of the mine, which is about 200 meters underground, and data were collected over a period of 60 days. You can see some snapshots of our detectors on site after shipping them overseas, positioning the detectors, and then leaving them in place in drifts underground for recording over the period of time. I should note that with this multiplicity of detectors and this depth of only about 200 meters, the period of 60 days was in fact significantly longer than it needed to be. But nevertheless, it allowed us to develop very high resolution images of the structure over that period of time. So if we look at the radiographic images that we developed then over the lifetime of the project, shown here are 4 of them. I'll explain them briefly and then note some of the key findings that you should be pulling out of this representation of the data. So these radiographic images have a coordinate system where you go top to bottom is south to north, or north to south, sorry, and left to right is west to east, so that if you're looking at 0, 0 in these images, that's looking straight up at the sky from the Muon detector underground. The color code, so from blue to sort of orange or pale blue or pale brown, is increasing significance of extra density in the data. So the really bright spots in the data, which are the colors, are indicating which pixels or which directions in the Muon data we're seeing significant extra mass between the detector and the surface, compared to an assumption of a geology which is uniform. Then the overlay, which is the transparency layer, is showing the expectation that we would have for the shape of the data if we assumed a simplistic model of a sulfide deposit. And so a key thing to extract from this is that in all the images, we're mapping the expectation quite well, and in particular, the highest significance of extra density is really showing up near where we expect it to be. But there are subtle geometric variations, which is not unexpected given the fact that the model being compared to is highly simplistic. can also represent the data in a different way. This is a polar projection of the data. So this might be more familiar to some of you. This is a projection where the center of the image is looking straight up at the sky. And then the upper hemisphere field of view going from west to east is basically this flattened circle. So increasing angles with respect to vertical are going in the rings emanating outward from the center. And so what's shown in the image on the left is, again, the extra mass significance. So it's a slightly different color scale, so it's a gray scale, but basically the same thing. So darker is where we have a significantly extra mass in the image. And then the blue contour is the expected contour from simulation of the simplistic deposit. If we're looking at the right, it's a slightly different presentation of the data. Here is, instead of looking at the significance of the extra density, we're directly measuring the extra density in grams per cc. And then we're shading it by a brightness scale, which is corresponding to the significance. And the reason we do this is because at the periphery of the image, where you're extending at quite large angles with respect to vertical, you're going through very, very long distances of the rock, where the muon data is quite low, and therefore the statistical uncertainties are high. And so it's important to damp the sort of fluctuations in the direct measurement of anomalous density in those locations. So, I mean, summary again, it's a different representation of the data, but the density anomaly we saw in the field data corresponds very closely to what would be expected if there was a nickel deposit there. We then did a sort of blind inversion, and although we had some a priori knowledge that there was a deposit there, this was in no way informing the inversion. And in fact, the density block model was not available until after we had done completed the survey and presented the results. And so there's a couple of surfaces and voxel sets in this model that I'm representing here, so I'll walk through them slowly. First, the block model is derived directly from drill data from many hundreds of drill holes through the area over years of exploration and delineation. The sulfide shell model is this wireframe that's orange, sort of vertically disposed, as you've also seen in the previous images. And then the voxel inversion from the muon data, incorporating no prior constraints or other geophysical data, is shown. And that's the red isosurface. So you can see it corresponds quite well to the density block model. In particular, it maps the lobe coming out of the sulfide shell off to the right on the rightmost image, which is clearly mapping sort of the disseminated sulfide off to the side. If you look at a plan view of the data as well as a slice to the voxel inversion, you can see it conforms very well to the ore shell model. So very high resolution 3D density model matches the density block model from drill data and also matches the simulation very well. So that's the Cliffs mine. I think some of you may have seen this one already, but I'll recapitulate it here and just very briefly. This is a case study we completed in 2018 at the McArthur River uranium mine in Saskatchewan, working with Orano. And here we looked at a compact uranium deposit at 600 meters depth. The comparison on the left is the field data, a slice of the voxel inversion coming from the Muon Tomography data, and compared to the ore shell model derived from extensive drill data. So you can see very good correspondence to the intersection of the ore shell with that slice of the voxel inverse model. You can also see a comparison to the simulation on the right. And this is basically forward modeling and then inverting the simplistic model of the uranium deposit. You can see some dissimilarity, but broadly speaking, very good correspondence. And the dissimilarity is actually explained by looking in more detail at the drill data. And in the drill data, we can see that the density is higher near the top of the deposit. And we're able to map that in the field data from the Muon Tomography survey as well. So not only are we locating the deposit, but also mapping the variations of density within it. The final one I'll present on mineral exploration is a lead zinc mine in Ponderae, Northeast Washington State. This is with Teck. This was a blind Muon Tomography survey that was performed there at about 600 meters depth with 4 sensor locations. It would have been extensively drilled a priori, but none of that was incorporated into the analysis. After we reported on the data to Teck and confirmed that what we were seeing matched well with their expectations, we then circled back and combined 5% of the drill data with Muon data and did a sort of a joint interpretation or joint inversion or constrained inversion, depending how you used the terminology and produced a quite compact inversion model or inverse model that corresponded very well with the ore shell derived from 270 plus holes. So with that under our belts, I think it's worth looking forward a little more now to the borehole detector progress, both what we've managed to achieve and also where we're headed with this. So the development of the version 3 has been going on for some time, from the very early stages of the project conception, envisaging eventually that we would be developing a borehole system for greenfield and near mine exploration. So this is leveraging the commercial trials in mining, the partners of which we are quite thankful for, and also the experience that afforded us in developing Muon survey design and parameters that would really govern the evolution of our detector platform. So we've been doing some years of system design and development, prototyping in a lab, looking at subsystem and system levels to really nail down all of the parameters of the design. And we're happy that the detector system is now working end to end. We're able to detect muons and map them through the whole chain of complicated, high-speed, low-power electronics. We're just now in the process of completing the final revision of the circuit boards. These have been fabricated and are being tested in the lab. And we have a doubling deployment going on, in fact, right now, testing the deployment of our sensors in a field location. So the production of our units begins in February, so coming up next month. And our first deployment is slated for March. It's very close, we can almost taste it. Looking in more detail at the specifications that have arisen from our market involvement, we decided to aim for an HQ-sized device. This is important to be able to meet sensitivity requirements, but also to afford us significant market inroads. So the device is less than 8.9 centimeters in diameter and about 4 meters long if we include centralizers, about 3 meters long without. It's low power, so amenable to remote locations where we have only solar panel access or wind turbine. And it's designed to be low maintenance, to be deployed over the intervening period between exploration seasons and allow us to just connect to the device remotely, continuously offloading data and analyzing it, but not having to physically intervene. With a pretty good non-operating temperature range that will be amenable to most deployments and capable of handling high hydrostatic pressures, so depths under the water table of many hundreds of meters, but still being maneuverable on the surface with a relatively low mass and robustness, and being durable with corrosion-resistant housing and using industry standard cabling and other hardware to really make sure that the device is robust underground. So in terms of our early access, we have published our first early access customer being Orano. We partnered with them at the McArthur River survey, of course, some years ago, and they're keen to get this going in a borehole for their exploration program. This will be deployed in March at one of their sites, and we'll be imaging a compact uranium pod. And as I mentioned, we've already shipped out a set of our detector systems for pre-deployment tests, actually this week. And so one of our teams is in the field completing those tests as of today, and they've gone exceedingly well. So we're very much looking forward to getting that first test underway. And data acquisition will proceed over the summer months with a project completion by fall, and then leveraging that going into more commercial, broader scale operations thereafter. In addition, an intervening period with a number of other early access partners that we're working on, and those are still under NDA, but we're very hopeful that those will move quickly, and very excited about the progress we're making there. Looking now back at applications of the borehole Muon Tomography capability, once this comes fully online in commercial capability in fall of 2021, after the early access programs have wrapped up, we're looking at focusing primarily on mining, in particular mineral exploration and block cave monitoring, with secondary markets in oil and gas and national security as they support our growth in the mining sector. And then longer term inroads into infrastructure. So looking here at things like dam monitoring, dam structures, dam cracks, and also construction, for example, tunnel boring examples. For mineral exploration, zooming in a little bit, we've looked at a number of commodities and exploration stages to see where this technology fits best. We have a sort of a sweet spot highlighted in bright orange here, and this is where we have significant density contrast. So the commodities here are base metals in massive sulfides, MBT type deposits, as well as some others, including also compact uranium targets such as at McArthur River, so unconformity type deposits that are high grade. So these are where we have significant density contrast, and we've also completed field trials. There's of course a whole suite of other commodity types and deposit types where there are still significant density contrast, but where we haven't yet got completed published field trials, and we're seeking partners there as well to carry out and understand our capabilities. With the borehole tomography detectors coming online in the next month or so, we'll really be opening up greenfield exploration stages, but we also, of course, have applicability in brownfield, both with the gallery style sensors or V1, but also leveraging boreholes in mine and near mine to extend known ore bodies and to look for near mine new deposits. I've already mentioned the constraints on depth. I think our sweet spot is in the hundreds of meters down to a kilometer. That's a good rule of thumb. And of course, it's dependent on target size and density contrast and other scenario configurations. One of the things that differentiates muon tomography from some other techniques is the fact that it's relatively insensitive to some of the complications that other techniques are sensitive to, which allows it to be used maybe in some broader contexts. So for example, conductive clays and overburden or existing infrastructure are all basically not impacting muon tomography measurements. And because it's a passive technique, it's also capable of being used in environmentally sensitive areas. So just to reiterate a rule of thumb on applications, and I think I mentioned this before, but I think it's worth keeping in mind that a density contrast of about 0.2 grams per cc, less than a kilometer deep and greater than tens of meters in spatial dimension is a place where muon tomography can perform imaging that's relevant for mineral exploration. A way to look at this in a more quantitative sense is to look at a particular scenario. This is very similar to the sulfide deposit I showed earlier, where we looked at the structured mesh inversion. And so here we're doing a search for a synthetic massive sulfide in a customer-driven scenario. So I'm very much informed by real-world exploration program. And this is at about 500 meters deep with a search grid of 400 meters by 140 meters. 35 meter by 35 meter grid is shown for reference. In this sort of plan view, it was quite reasonable to expect sort of 35 holes in searching for the location of what would seem to be some kind of conductive activity. And there's holes that are intersecting and holes that are not intersecting, totally 35 holes. If we look at a case where we use the Ideon Muon Tomography detectors in this search, leveraging only 3 holes and 16 detectors, we would be able to save roughly 35 holes drilled to be able to discover the deposit, 27 of which would not have been used in resource definition thereafter. So of course, it's fair to say that even after discovery of location of a target, there's of course subsequent drilling to understand the grade continuity, et cetera, but you can see a significant savings in the drill holes that are not intersecting the deposit. And so in this particular case study, we're looking at significant savings of 5 million compared to just conventional drilling scenario. So with that, I'll wrap up. In summary, I hope that I've excited you about muon tomography. It's comprising 10 years of focused R&D in the field trials. And it's worth reiterating our thankfulness to industry and academia and government that have really shown a lot of support to bring it to where it is today. I think it's safe to say that we can add a lot of value to exploration processes. We have muon tomography, greenfield and near mine coming on stream in both cases with our borehole configuration. We have advanced inversion methods, and we're also bringing to bear AI and integration with other geodata to really add value to the whole exploration process. We're super excited that we're about to hit the field in the next month or so. Super excited, but super stressed and busy as well, fair to say. And our early access program is filling up. But of course, if you're interested in pursuing potential applications, I invite you to connect with us via our web link in the footnote below, and we'll follow up. So many thanks, and I guess I'll open it up to questions.
Yeah, wonderful. Thank you, Doug. It's really nice to see just how much you guys have accomplished in the past few years since your last BCGS talk. We've had a number of really good questions in the chat, which have been answered by Don Furseth, so I may skip reading those ones out. So I'll read the last one here. Brendan has a question about hole conditions. Have you tested surveying through casing, and can you account for this in your modeling?
Yeah, good question. You know, in terms of longevity of the detectors, our preference is probably to have cased holes because it guarantees that after some months of deployment, we can pull the detectors back to surface. Although, of course, in competent holes, using an uncased hole is perfectly feasible as well. In terms of affecting the data itself, casing will have basically no impact. We're talking about less than a centimeter of material compared to the hundreds of meters of rock that the muons are traversing to get to the detector. And so that impact on the muon intensity is vanishingly small. So it's not an issue.
Excellent. Thank you, Doug. We have another question that's came in. Can you explain more about how the data is processed from Muon Tomography?
Sure. There's a bunch of sort of pre-processing that goes on that has to do with really the internal components of the sensor and how the data is presented to us. And it's not possible to go through some of that without really opening up the IP of the detector and really understanding the nitty-gritty of particle physics detection capabilities. But let's just assume for a moment that what we get out of the detector is a time and a couple of space points in the detector where we had a candidate muon event passing through. So what we do is we take those space points through the detector, often a very short path length, so we have to have very high spatial resolution. But we connect those points to make sort of a linear estimation of the trajectory of the muon. So based on that linear track fit, we then know where the muon came from to be able to pass through the detector, and we record that trajectory in a radiographic image where each pixel is a direction. And so we populate these bins or these pixels with the number of muons observed over a period of time, and that gives us a muon intensity image for a particular detector. And so we can decide a priori how fine we want to look at that. We can either choose a coarse resolution if we're looking at a short time scale, or if we're going over a broader time scale, we can really make very small pixels and have very high resolution imaging. That's a matter of survey design. But in any case, we come up with a radiographic image where each pixel shows us the average density in each direction in the whole field of view. And then we go through the inversion methodologies that I walked through in the slides. Hope that helps.
Great. Thank you, Doug. Graham has a question about how are you guys using AI at this stage, and where might that be going in the future?
Yeah, it's a good question. We've been using AI in a number of ways. Some of the the case studies I've shown you sort of involve AI in the background. I haven't gone through in detail of that, but in particular, the case study for the structured inversion and also the linear feature detection or the drift mapping for mine infrastructure. Both of these case studies, we leveraged AI for image processing capabilities. We're also very happy to announce or report that we've recently brought on board Max Howarth, who's our director of AI. So he's coming from applying AI in geoscience for the past few years at a very high level, leveraging IBM Watson for applying AI to geoscience. And so we're bringing to bear AI into really data integration. So combining disparate geophysics data sets as well as geological data, like drill assay data, to do 3D drill targeting and also 3D interpretation. So it's both an area that we've been leveraging in the background in powerful ways already, but also an area that there's a lot of future activity in developing new applications and capabilities. that helps.
Excellent. We got lots of questions for you, Doug. You're definitely stimulating some interest in the crowd. The next question is from Chris. How sensitive is the modeling to orientation errors of the detector down a hole? And how does this compare to the accuracy you could achieve with the orientation of the probe?
That's a very good question. So indeed, that's one of the important constraints or considerations we put into the design. So we have a high resolution IMU installed in the detector that locates it. And then of course we have surveyed holes, but there's another feature that we can employ from the data, which is the fact that muons are coming from the sky. And by combining all of these information bits, we can have a very high resolution understanding of where the probe is pointing. And we can track that over time. However, one of the key things I've mentioned, I talked about the length of the detector and using 4-meter length with centralizers. So we do envision using centralizers to help stabilize the rotation of the detector and hole. And that's really to guard against drift in the IMU over long periods of time. But that's a good question. And I think we have a fairly robust handle on being able to know where it's pointed at any given point in time during the duration of the project.
Great. What, for myself specifically, what would a centralizer be in this case?
Yeah, it's like basically a bowstring. So you can imagine it's like a thing that sits on the other end, and there's sort of bowsprings coming out, so that sort of pushes up against the ID of the borehole, and that keeps it from rotating just with friction as we position it in place.
Okay, so actually physically holds the sensor.
Yeah, exactly.
Great. Sergio would like to know, what is the typical opacity values for a VMS deposit? If I'm not asking that correctly, Sergio can certainly unmute himself and explain a little bit in more detail.
Yeah, I think I understand the question. So opacity is go ahead, Sergio.
Yeah, it's like resistance. I mean, mass density is the physical rock property, and resistance is the physical rock property plus some geometry. Go ahead, Doc.
Yeah, exactly. So opacity has a geometric dependence. So the orientation of the deposit, for example, will affect the sensitivity because it's the path length through the deposit that counts in conjunction with the density contrast. So a typical VMS deposit will have a density contrast of, say, let's take a figure of merit of 1 gram per cc. And for most VMS deposits, we're looking at, even if they're flat lying, thicknesses of, say, 10 to 20 meters. So typical opacity addition from having a VMS in the field of view compared to just the host rock is sort of 20 meters of water equivalent. It's often a unit that we use. So that's an opacity value that we can measure. So our sensitivity to that measurement will depend on the depth of the detectors and the deposit, and also the exposure time of the survey.
Fantastic. Is there any benefit to using surface detectors in conjunction with borehole detectors? Yeah,
that's a question that comes up quite often. In principle, it can add some value in being able to normalize the muon flux over the lifetime of the project. In practice, the variations that come from atmospheric changes, specifically seasonal changes, are small and only really affect or primarily affect the low energy component of the muon spectrum. So I showed you that graph very early on in the slides where you look at the rate of muons coming into the surface of the Earth across the whole span of energies. And it's really only the low energy part of that that's primarily affected by variations that are seasonal or related to solar winds or geomagnetic variation. And those are filtered out in the first 2 meters of rock, so really aren't informing our measurements underground. So although in principle there is some benefit to having a normalization measurement on the surface, in practice it's rarely needed. In terms of directly tracking individual muons that hit both the surface detector and coincidentally an underground detector, this does open up different measurement capabilities, but given the fact that your solid angle for hitting 2 detectors separated by hundreds of meters is vanishingly small, it will only really give you like a pencil-like sensitivity directionally instead of a large opening angle view. Hope that helps.
Ross, you muted yourself.
Well, thanks, Dennis. A question from Jerry, kind of looking at like the opposite problem here, the void detection. But have you considered using the borehole detectors for, let's say, looking for voids in the Great Pyramids or other?
Yeah. If there was commercial interest, that's certainly something we could do. But there has been certainly academic research in this application. So I didn't mention it in the talk, but just a couple of years ago, there was quite a splash in the media in the Great Pyramids, Giza, using Muon Tomography with a couple of different approaches. Some academic researchers from Japan and France and Italy, I believe, were actually able to demonstrate very strong evidence for a hidden void in the pyramid. That's still, under further discovery or further investigation, because as you can imagine, drilling holes into the center of a cultural artifact like that to confirm something like that is taboo. But yeah, it's certainly been used, and historically has been one of the earliest attempted applications of the technology. So void discovery, void delineation is certainly an application that is of interest to us, and one of the obvious candidates from a commercial standpoint is in infrastructure, so a particular tunnel construction, and being able to map upcoming voids during the underground tunneling, where ingress of water from voids can be a serious issue.
Great. No, that sounds very interesting. What's the maximum solid angle that the detectors can measure? Yeah,
it's a good question. Figure of merit, I would say 60 degrees in all angles. So the total opening angle is 120 degrees. And that's sort of a cone-like shape emanating from the detector up to the surface. So it does depend a little bit on what coordinate system we use to look at the data, whether it's rectilinear or polar. But yeah, basically a cone field of view going from the detector to the surface with a total opening angle of 120 degrees.
All right, fantastic. Now, a question from myself. Is there any sort of seasonality with the incidence of muons that would need to be taken into account with survey design, say different muons in the spring and summer versus maybe the fall and winter?
Yeah, there is some variation. I hinted at that a little bit with the question about normalizing the flux. What happens is the atmosphere gets progressively or seasonally thicker and thinner from a muon's perspective, gets denser and less dense. And that affects the rate of production of muons and also the rate of filtering of the low energy muon. There's also geomagnetic variations, both from solar winds and also spatially across the surface of the Earth. But all of these things really only affect the low energy part of the muon spectrum. So muons have low energy and are absorbed or stopped fully within a few meters of rock, and so don't affect the intensity that we measure at tens or hundreds of meters underground.
Great, yeah, that definitely clears it up. Looks like the last of the written out questions, so I wouldn't mind opening it up to anyone else that has any questions, if they want to maybe unmute their mic and do it to be a little bit more social, kind of at the end here. Looks like Dennis might have a question.
Well, I was just going to thank the speaker, but let's wait for any other questions. Or
Sure, I've got a question. It's Kyle Patterson here. Hey, Doug, I've got a question about the MacArthur River example. And I'm wondering, how did you handle the noise from the naturally occurring radiation within the mine infrastructure?
That's a very good question. Looking back at the survey, we spent a lot of time understanding this. I could go into a whole explanation of how the survey unfolded there. Let's not look too closely at how the sausage is made. But in the end, what we did was we did a host of measurements to really confirm to ourselves that the background radiation coming from the radon, which is part of the uranium decay chain that pooled around the detectors, especially when the ventilation shafts or the ventilation system was shut down, that we were able to filter it out with 100% efficiency. So we're able to really separate the muon signal in our detectors from that radiation source. And the reason was that the muon signature, as it passes through the detector, leaves a very particular amount of energy as it hits. So we can record the strength of the signal. And that strength of the signal is very different than for the lower energy electrons and alphas that come from natural radiation backgrounds from, say, potassium or radon. And so it allows us to separate those two sources of radiation signals in the detector. So if you want to follow up on more details on that, just one more thing there. If you go to our website, there's a case studies section, and we have our paper published there in the American Geophysical Union, and there's a whole section in the paper actually devoted to that exact issue. So you can follow up in more detail there if you'd like.
Another question, detecting spurious radiation. If you remember the ice cube flap about upward propagating cosmic rays, I was just curious if you folks record any events that are coming from inside the Earth.
Yeah, so the primary source of muons coming from the far side of the Earth is actually an interaction with neutrinos. So it's getting a little particle physics geeky on you, but given the fact that you've quoted ice cube, I feel I have some latitude here in answering. But neutrinos are another fundamental particle that interact very, very weakly. And in fact, there's some particle physics experiments where they fire beams of neutrinos through hundreds of kilometers of rock, hoping to see single event from the far end. So, and because we have neutrinos coming through the Earth, especially from the sun, there's some possibility that neutrinos, just as they're coming to our side of the Earth from the far side, will interact and essentially create a muon. And so there's a source of upward coming muons from that. But if you compare it to the rate of muons coming from above, from cosmic rays, it's vanishingly small. So that, in fact, that upward coming muon source is sort of what sets a practical limit on the depth, because at some point you're so deep in the Earth that the upward coming muon source is significant compared to the cosmic ray source, but that's multiple kilometers deep. So at the depth range we're looking at, it's a vanishingly small impact.
Well, thanks. That's really interesting.
Well, Ross, I think we've taxed Doug long enough, haven't we?
Absolutely. If you have a few words, definitely jump on it.
Yeah, well, I got a question actually first. There are other labs around the world, certainly, and people working on muon research. But I'm curious, is there anyone else developing muon technology for mineral exploration, or is this, do you have this field to yourself?
There are some, well, I have to wear my commercial hat and tell you, in all honesty, there are some copycats out there. We have I think a very particular advantage having coming out of Triumph, but also having the mining ecosystem in Canada that's really given us a leg up in developing this. But there are companies in France and Finland that are also pushing this technology forward. But based on, we meet each other at conferences, not so much recently, but in the past, and we certainly track their progress. And I think I can safely say with provability that we're leading the way there. But of course, it's clearly, as we open up the market, it's going to invite more growth in the field. So that's certainly the future of muon tomography, I think, as it becomes more of a standard approach.
Well, Doug, it's just extremely exciting stuff. I'm just fascinated by the whole aspect of it. I remember getting into geophysics in the first place. You're thinking applying physics to geology, and you guys are doing it at the highest level possible. This is kind of the sexiest geophysics applied to geology that I can possibly think of.
Yeah.
But,
it's certainly a benefit to have a sexy geophysics like this. But in the end, of course, it's going to be proven by what it's able to do practically. And that's really what we're aiming for.
You seem to be on the way for sure. Yeah. And it's going to be exciting watching the development over the next few years, how it goes. Really interesting. thank you very much for a wonderful talk, and thank you all for attending. We had a very good number today, and appreciate you all turning out. And please come again in February. I think we'll have an exciting talk in February as well.
Thank you very much.
Yes, absolutely. Thank you everyone for coming out.